I was to be a ham. Jem said he would escort me to the school auditorium. Thus began our longest journey together.
Hi everyone. Today we are going to start looking at topology and L'Hopital's rule. So this video is going to be just a very superficial glimpse at what topology is. Nothing I think is going to make much sense, but the goal here is just to ask some questions and look at maybe some examples to get our imaginations kind of flowing. And then in the next few weeks, we're going to be doing topology in more detail. So first, though, is the reason that we're going to be talking about topology now at all. So the last video in this series about limits was supposed to be about continuity before we move back to multivariable calculus. But in the last couple of videos, as we've been talking about limits, we've been talking indirectly about one of those details that we learned in high school that is so cool, it makes you love math: indeterminate forms. And I don't know about you, but I've always been fascinated by them. Like 0 over 0, infinity over infinity, infinity minus infinity, infinity times 0, and 1 times infinity, and then infinity to the 0, and 0 to the 0, right? These are always just interesting and baffling and fascinating. So in studying differentiation, at one point we learned about something called L'Hopital's rule, right? Now, myself, the only thing I came away with from undergraduate calculus regarding L'Hopital's rule was the phrase L'Hopital's rule. I wouldn't have been able to recall what it was about to save my life. What it's about, in fact, is indeterminate forms. So I think that for a lot of us, for me at least, I realize now as I get older that our math teaching is not very good. It's rote and not very insightful, and L'Hopital's rule was one of those things. It's actually really cool, and when you're fully interested in how limits work and real numbers and real analysis, then L'Hopital's rule is really cool as well. So before we go back to multivariable calculus, since we're already talking about indeterminate forms, I thought it would be fun to take one video to learn L'Hopital's rule again for the first time before finishing up with continuity. So the reason I'm saying that we've been talking about indeterminate forms is that in the last video, when we were looking at limits as x approaches infinity, like we did one example, 3x squared minus x minus 2 over 5x squared plus 4x plus 1, right? And this, as x approaches infinity, it's infinity over infinity. So how we deal with that is what we were talking about last video. So what is L'Hopital's rule? The last time when we were looking at the limits as x approaches infinity, we derived a new rule. The limit as x approaches infinity of 1 over x to the r equals 0 when r greater than 0 is rational. So this rule allowed us to calculate weird things like this using the limit laws. Because as it is, as x approaches infinity, this is just infinity over infinity. And infinity over infinity, what it means to be indeterminate is it could have any value. It could be 0, it could be infinity, or it could be any finite number in between. But using our trusty algebra, we're able to manipulate this function into something that will allow us to use our new rule. So in this case, what we did is we divided the top and bottom by the biggest power of x. So if we divide through by x squared, we get this new expression. And we can see that all of the extra terms are 0. So this just ends up 3 minus 0, 5 plus 0, and we have 3/5. So we talked about this last time, how cool that is, that this is infinity over infinity, and we end up with 3/5. And then we looked at some other ones as well. Another example was the limit as an x approaches infinity of the square root of x squared plus 1 minus x, which this is in the form of infinity minus infinity, right? This goes to infinity, this goes to infinity. So again, we can't calculate this using our limit laws, but using algebraic manipulation again, we were again able to rewrite it so that we could calculate what the answer is. So the thing is, this technique of algebraic manipulation is limited to a small set of functions. And we can't manipulate every function in this way to get it so we can use our new rule. So just for instance, the limit as x approaches 1 of ln x over x minus 1. So this has the form 0 over 0 because the limit of log x as x approaches 1 is 0, the numerator is 0, and 1 minus 1 is 0. So this comes out to 0 over 0, which is another indeterminate form. But there is no algebraic manipulation we can do here. So L'Hopital's rule allows us to calculate a much larger range of indeterminate forms than we were able to do just with algebraic manipulation. That's what L'Hopital's rule is. So L'Hopital's rule states that, suppose that f and g are differentiable on an interval I containing a, except possibly at a, and that the derivative of x does not equal 0 near a, except possibly at a. Suppose that the limit as x approaches a of f equals 0, and that the limit as x approaches a of g is 0, or that the limit as x approaches a of f is plus or minus infinity, and the limit as x approaches a of g is plus or minus infinity. Then the limit as x approaches a of f over g equals the limit as x approaches a of the derivative of f over the derivative of g, if the limit on the right side exists or is plus or minus infinity. In other words, we have an indeterminate form of type 0 over 0 or infinity over infinity. Okay, so notice that we're going a little out of order here from normal calculus texts, because usually after learning about limits, you have to learn about derivatives and then go on for 2 chapters about how to calculate derivatives and various applications of derivatives before we finally get to L'Hopital's rule. But I'm assuming we already know the rules of differentiation, so the statement of this rule shouldn't be that difficult to understand. It's limits, I think, that we needed brushing up on, and when I say us, I mean me. Now, understanding why this is true might take us a little bit of effort, and we're going to look at this more. But understanding the statement, I think, isn't difficult at all if you understand what derivatives are. So, why topology? What's this have to do with topology? I was thinking, when I decided that I wanted to do a video about L'Hopital's rule, I was thinking that we haven't done an interesting, rigorous proof in a while, and that this would be a good one to do. Let's just take a video or two to prove L'Hopital's rule, because it's cool and interesting and about indeterminate forms. So I thought that in order to finish this section on limits, we would just prove L'Hopital's rule. But it turns out that is a very difficult thing to do. By trying to prove this little rule, we've stumbled upon the very deepest foundations of calculus, foundations that are deeper than anything our calculus book will ever even hint at. There's an entire substratum on top of which calculus lies, they're like orc tunnels under the misty mountains that the calculus books never mention, and that's called topology.
Where there's a whip, there's a way. Where there's a whip, there's a way.
So the proof is built on a tower of theorems that we need to prove in order to get to L'Hopital's rule. So the rule itself is pretty straightforward, but it requires the mean value theorem. And not just the mean value theorem that we learn in our calculus class, but the generalized mean value theorem. This is also called Cauchy's mean value theorem. So most of what we learn about derivatives and maxima and minima, what we spend so much time in calculus class learning is how to use the derivative to find the maximum right there, right? It's where the derivative equals 0. And that all depends on the mean value theorem. Like most of the stuff that we learn about applications of derivatives depends on the mean value theorem. And proving the mean value theorem is pretty straightforward, but it relies on another theorem, Rawls' theorem. And Rawls' theorem is pretty easy to prove, but it relies on the extreme value theorem. So now we're going along fine, and then suddenly we just hit a brick wall. This is where the powers of undergraduate calculus completely break down. To prove the extreme value theorem, we need topology. So specifically, just to go on with what we're going to have to prove here, the extreme value theorem requires a boundedness theorem, and the Bolzano-Weierstrass theorem. By the way, I think it's interesting that I had never heard of Weierstrass before we started doing these videos, and he's hugely important, but it seems like the things that he worked on were more sophisticated than the guys that we usually hear about, like Euler and Cauchy, at least maybe exclusively more sophisticated. So we don't learn about him. I don't think he's ever mentioned in a calculus book, but he keeps coming up here when we're getting toward what we need to know about, which is elliptic curves. And then the Bolzano-Weierstrass theorem also implies the intermediate value theorem, which this is another one. The intermediate value theorem is a theorem that is mentioned in the section about continuity. But again, the calculus book just says, well, proving that's too hard for this book, so we're not going to bother. They just hand wave how we get to this. So this also requires topology, and this theorem is very interesting because it's very easy to understand, and in fact, it's hard to imagine that it's not true. If we have a continuous function on an interval AB, then there must be a value x in AB such that. So all that says is, if we have some function here, and it starts here, and goes up to here, then there has to be some value of x inside this interval that will give you an f of x that's between f of a and f of b. So that's extremely obvious. You can't imagine how that's not true. And in fact, once again, this is what we've been talking about way back when we started looking at parameterizing a curve. This is what makes parameterizing a curve possible, because if you have 2 points and a line between them, then you've got to, if they're, quote, continuous, there's got to be every value in between. What our textbook tells us is, that's obvious. We don't even need to bother proving that. But proving this claim is actually very difficult, and it requires us going back all the way to the beginning of our construction of real numbers. In order to prove the intermediate value theorem, and hence, up the chain, L'Hopital's rule, we're going to have to go deep into the abstract structure of real numbers, which again is what topology is all about. Okay, out of paper. Okay, so what is topology? When I was little, my parents had a subscription to the Time and Life Science Library. And actually, they must have had the subscription before I was even born, because I don't remember us ever receiving one, but we had them. And one of the books in that series is mathematics. That book is my earliest memory of like non-grade school mathematics. And that book had a section on topology. And I don't remember it explaining what topology is, but to this day, I remember the examples. How a donut can be morphed into a teacup, that's one big example. And the other one that I was fascinated by was that if you're wearing a vest and a jacket, and they're both unbuttoned, you can take the vest off without taking off the jacket. And I actually remember when I was little, I used to put on my dad's suit to see if I could do it, take off his vest without taking off the jacket. And it's true, you can do it. So I realize now that there's an adult version of this, which is whether a woman can take off her bra without taking off her shirt. And if you can get it unhooked, was she ever really wearing the bra at all? This girl would not have been able to do this without topology. I learned about that when I was 7, and I'm not sure that I understand a whole lot more what topology is today. So there are 2 sorts of branches to topology. One is the fun the fun geometry of continuous deformations, and that's what the teacup and the vest are. The essential thing about the teacup and the donut is, from a topological perspective, they both have a hole. They can be continuously transformed, but the one thing that you cannot get rid of by transforming it is to get rid of that hole. And by the way, if you remember, this is not an arbitrary issue. This is actually that transforming that donut is actually central to the proof of Fermat's last theorem, because we talked a few videos ago about an elliptic curve and how in projective space it comes out here and meets at infinity, and that this basically, oh, not this one, this one, comes out here and meets at infinity, and this basically has the topology of a donut. And then we compared that to a sphere and how topologically a Riemann sphere and a donut do not have the same topology, so you cannot transform one into the other. And that proves that Pythagorean's theorem doesn't work for powers greater than 2. So this isn't just arbitrary. So the other side of topology might be called maybe the abstract side, or the mathematical side, or maybe the, I don't want to say the algebraic side because that has kind of a specific meaning, but like the mathematical side as opposed to the geometric side. You can't really prove a mathematical concept by watching a girl take off her bra. So I'm going to go ahead and tell you the definition of topology, just so we can see it. So here's the mathematical explanation of how a girl can take off her bra without taking off her shirt. No! So a topology on a set X is a collection T, that's supposed to be a recursive T, of subsets X having the following properties. First, the empty set and X itself are in T. 2, the union of the elements of any subcollection of T is in T. And 3, the intersection of the elements of any finite subcollection of T is in T. A set X for which a topology T has been specified is called a topological space. This is, I believe, the most bizarre thing that we have encountered so far, right? I think I'm going to be able to explain what this definition is getting at, so you'll understand it from now on. Now, chapter 2 of Rudin's book is called Basic Topology, and it contains all of the topology building blocks that we will need to ultimately prove L'Hopital's rule. We're going to go through this chapter in detail. Now, I'm going to say something controversial here. I think that Rudin's Principles of Mathematical Analysis is a terrible book. Its reputation as a classic, I think, is rather absurd. Here's what I mean. For example, chapter 2 is called Basic Topology. Nowhere in the book does he even explain what the word topology means. The word topology is not used one time in the chapter about topology. The book simply fails as an educational tool. It's almost utterly devoid of motivation. Once you understand the subject, then if you go back and read Rudin again, you might see that, oh yeah, he did mention this here. But the important details are always mentioned in passing, if they're mentioned at all. But we're going to see if we can't decipher this chapter of Rudin on topology. So what Rudin does in his book is he only presents the topology that we will need in order to move forward with calculus. So as abstract as this chapter is, he restricts our study to one kind of topology, which is called a metric space, without explaining, of course, what metric spaces are or what it means that they're one kind of topology. But we're going to get back to that. So Rudin had to decide how abstract to get, and I think that the choice he made was a bad one. So here's what he says. He says that although we shall, in later chapters, be mainly interested in real and complex functions, i.e., in functions whose values are real or complex numbers, we shall also discuss vector-valued functions, i.e., functions with values in Rk, and functions with values in an arbitrary metric space. The theorems we shall discuss in this general setting would not become any easier if we restricted ourselves to real functions, for instance, and it actually simplifies and clarifies the picture to discard unnecessary hypotheses and to state and prove theorems in an appropriately general context. The domains of definition of our functions will also be metric spaces, suitably specialized in various instances. It sounds to me that he's not capable of understanding that he understands it because he understands it. But when you see this stuff for the first time, it's completely baffling, and he's not motivating it at all. I actually just think that it would be better if he had just gone along with real numbers, because you can prove all these things just using the properties of real numbers, because all he's doing is sort of describing real numbers as an example of this broader set. We could go back in a topology class and sort of fill in the abstractions and just go with how these theorems work with real numbers for now, where they're more motivated. He cares more about the fact that it simplifies and clarifies the picture. It doesn't simplify and clarify the picture. It might simplify the theorems, but that's not the same thing. Topology is fun. It's interesting and very strange. So since he does it, I think it'll be good for us to go ahead and go through it and try to understand where he sort of doesn't do too good of a job of explaining things. So he made this chapter way more abstract than he needed to, but then he didn't go all the way and make it as abstract as he could by going all the way to the definition of what a topology is. So there are topologies that are different from metric spaces, which I'm going to talk about in a second. But introducing that fact would be too far afield to be educational. It would be just a morass of abstractions that don't have any connection to real numbers. So Rudin makes it as abstract as he can without, he thinks, losing meaning. But I think we can legitimately question whether it's pedagogically useful to abstract these concepts at all, rather than simply stating and proving them for real numbers. So the abstractions of topology are far more difficult, for me at least, to wrap my head around and get straight and comfortable with. But just these two concepts, limits and continuity, and hence all of calculus, require a great deal of careful analysis and abstraction to identify which concepts and properties are essential in a number space in order to prove the properties of calculus. So a big part of math is abstracting concepts from concrete examples. We've already seen the group structure of elliptic curves. Abstract algebra looks at the structure of number system, like addition and multiplication and so on, and asks what's essential. What if we had only one, what if we had a group with only one operation? That's what a group is. And then if we add another operation and make them distributive, then that is what rings are. And then if we make the second operation a group structure also, then that makes it a field. So that's abstract algebra. So the question is, what can we abstract out of real numbers and continuity and limits and so on? So the first thing, as I already said, is a metric space. So here's the thing. We spent several weeks constructing the real numbers, and we started by noticing that rationals have gaps, right? And we constructed the real numbers in order to fill those gaps. It seemed like that was all we needed to do in order to solve our problems, right? Because the question was, what's the solution to x squared equals 2? Well, the solution is x is the square root of 2. This isn't a rational number, so we basically constructed the real numbers in order to fill in those gaps. So we did that by making Dedekind cuts, right? So Dedekind cuts were defined as sets of rational numbers such that a cut, alpha, is not empty and it's not all of q. And if p is an element of alpha and q is another rational number, and q is less than p, then q is also in alpha, which means that cuts are bounded from above. And then 3, if p is an element of alpha, then p is less than r for some other element r in alpha. Cuts are bounded from above, but not below. So this whole thing is alpha. 3 means basically that there's no largest member. It gets closer and closer, but never hits the boundary. So that's what a Dedekind cut is. This definition was enough to fill in these gaps to make irrational numbers. But if you had a very sharp eye, you might have noticed that when we're talking about limits, we introduced another concept that we never mentioned here: distance. These definitions are pure set theory. They have nothing to do with distance. And yet, our definition of limit is that the limit as x approaches a of f of x equals L if the distance from f of x to L is less than epsilon whenever the distance of x from a is less than delta. That's what the difference means here. It's the distance between these two, right? So if we had a function here, and we have a, and then there's an interval here, then no matter how close we get this interval, epsilon, we can find a delta such that everything inside this interval is inside this interval, right? That's distance. Real numbers, as we constructed them, have nothing to do with distance. So we kind of introduced something else here. So even though it feels like limits follow directly from our construction because it's all about getting closer and closer to a boundary without going over and things like that, really there's something additional going on here. And this concept of distance is the concept that we're talking about when we talk about a metric space. So we all know what a distance is in real numbers. In one dimension, the distance between x and y is just the difference between x and y. And if you have 2 points in Cartesian coordinates, the distance between them is px minus qx squared plus py minus qy, square root of that whole thing, right? What is that? That's just the Pythagorean theorem. Here's the distance between the x's. Here's the distance between the x's, the distance between the y's. You square these, add them together, take the square root, and you have the distance from P to Q. So we know what distance is in Euclidean space. So abstractly, the definition of a metric space is a set X is said to be a metric space if with any 2 points P and Q in X, there's associated a real number D from P to Q called the distance from P to Q, such that the distance from P to Q is greater than 0 if they're not equal, and if they are equal, it's 0, and the distance between them is equal in either direction, so PQ is the same as QP, and the distance from P to Q is less than or equal to the distance from P to R plus the distance from R to Q for any R in X. And C, of course, is just the triangle inequality. So any function with these three properties is called a distance function or a metric. So a metric space is a set of objects with such a distance function defined on them. So the real numbers are a metric space with dpq equals p minus q, and in R2 it's what we just set up here. So the point, of course, of abstracting something is that there can be sets with different distance functions. So anything that we prove about a metric space generally will be true of real numbers as well as in many other contexts. So it's easy to overlook the fact that distance is an assumption that we're making about real numbers. In calculus class, when we're defining limits, we're just assuming that there's this distance function. It's not something we should be doing. We need to define what the distance means, and the Pythagorean theorem is only one possible way to do it. Okay, so that's topology, that's metric spaces. So what's wrong with continuity? So I already said sort of what it is intuitively, that if you have 2 points, basically it just, every value here is gonna have a value here. And more rigorously for calculus textbooks, what we're gonna learn next time is that the definition of a function being continuous at a point is that if the limit as x approaches a of f of x equals f of a, then f is continuous at a. And if a function is continuous on an interval, it means that it's continuous at every point in the interval. That's what continuous means, and that's what we're going to look at next time. So when we were constructing the real numbers, we knew that there were gaps in the rationals, right? Like square root of 2. And we filled in all those gaps. So we talked about the least upper bound property, and we constructed a number system that fills in those gaps. And we even proved that in some sense the real numbers are unique, like they're rigid, they're complete. So when what we showed was that when we added the least upper bound property to a set of numbers, then there's nowhere else for us to go. You can't make a bigger ordered field with the least upper bound property. So we thought we were done. We thought we filled in the number line. Now it's smooth, it's continuous. But actually, when we were talking about real numbers, we never actually mentioned the concept of continuous. And again, nothing in our definition and construction implies that the system is actually continuous. It just seems like that's like by filling in all the gaps, we made it continuous. But did we? So this definition just means that there are no gaps in the graph. Like if you have something like this, and then maybe there's even a point up here, this is not continuous because f of a does not equal the function as x is approaching a, and then here the left and right limits are different. So there are jumps here, so this function would not be continuous. So isn't it obvious that if a function is continuous from a to b, that every point in between, that there's going to be an f of x for every point x in between? Isn't that obvious? So yes, it's obvious, yes, but have we proven it? No. So we're kind of barking up the wrong tree here is the problem. Everything we're talking about here for the definition of continuity is necessary to continue building our derivatives, but it's not sufficient. And the important concept that's missing and the thing that the calculus books just skip over is the intermediate value theorem. And the problem is that with the definition that we have so far without something more, it still allows for gaps. Even though this is the definition of continuous, we could actually end up with a gap here. So in order to prove the intermediate value theorem, we're going to need something other than the limit as x approaches a equals f of a. So let me show you one example of how insane topology can be with an example where this breaks down. So let alpha be an irrational number. Then the function from rationals to rationals defined by f of x. So obviously this is discontinuous, right? It's just obvious. It goes up here, and then at alpha, it just jumps up one, right? No. According to our definition, this function is continuous. Over rational numbers, this is continuous. There's an obvious break here. But if we're just talking about rational numbers, our definition of continuous can't detect this break because the definition says that the limit as x approaches every value in the domain has to equal the function at that point. And the thing about rational numbers is you can make x as close as you want here, right? Just barely a gap here. But still, our definition of limits says that there's always going to be some neighborhood around x that allows the limit as x approaches this number a from either side to exist because alpha is in that gap. So for every number less than alpha, the rational numbers will never reach alpha. There's no biggest rational number less than alpha. That means that you can always make, no matter how close a gets to alpha, you can always make a delta small enough that point will be continuous. And then on the other hand, if you go bigger than alpha, there's no smallest rational number bigger than alpha either. So you can, if a is over here, you can still always find a neighborhood inside here that will make every one of these points, no matter how close you get to alpha, every one of them is continuous. So this function is continuous across this interval over the rational numbers. The point is, we're missing something here because what we want, the whole purpose of calculus is about these smooth, continuous graphs and functions. And they are smooth and continuous over the real numbers, and they're just hand-waving over what it is that we're missing. That's what the topology is digging into and has to get, to realize that it's like this definition doesn't work if it's over the rationals. There's something else than continuity needed in order to prove the intermediate value theorem for a set. So I don't expect us to understand this example well yet. It's just to give us a taste of the insanity of this topic, how easy it is to get tricked and fooled with this stuff. Remember, because we thought that the problem with the rationals was that there were gaps. So if we fill in those gaps, then it'll be continuous. But it turns out our definition of continuous is missing something because rationals are continuous in this sense. So it's important to understand, though, I'm not claiming that the definition of continuous in our textbooks is wrong. The point is that everything in undergrad textbooks is done within the context of real numbers. And so the proof of the intermediate value theorem is skipped over. If we just jump into the real numbers, then the calculus textbooks don't have to worry about it. But that's where we're backing up to examine what is continuity really. So this is the problem that we have to address before we can move forward with calculus. And it's the problem that we need to address before we can prove L'Hopital's rule, because we have to prove the intermediate value theorem in order to prove L'Hopital's rule. So there are several basic concepts of topology that we're going to need in order to prove the intermediate value theorem. One of them, obviously, is what a metric space is. We already went over that. Another one is compact sets. So compact sets are probably maybe the most difficult thing that you encounter in undergraduate math. So do you want to see just how bizarre compact sets are? If you haven't encountered them before, here's the definition of a compact set.
Fasten your seatbelts. It's going to be a bumpy night.
So, there you go. A subset K of a metric space X is said to be compact if every open cover of K contains a finite subcover. So I think that I'm going to be able to explain this in a way that will make it sink in intuitively, I think, for most of us for the first time. There are dozens of websites. There's even like an article that this woman wrote about how compact sets are the hardest thing to understand, and it took her years of going over the definition to figure it out, and then she finally did, and she's going to explain it to you now. All she did was basically repeat the definition. I didn't get anything out of it, but I think I have them figured out in a way that will make it jump out at you what we're talking about. So we'll get to that when we get to compact sets. And the thing is, compact sets are, at the same time, they're one of the hardest things. They're one of the most crucial concepts in real analysis. And then the other concept we need is connected sets. For a set to be connected means it cannot be represented as the union of two or more disjoint, non-empty, open sets. Okay, so here's the rigorous definition of connected. Two subsets, A and B, of a metric space X are said to be separated if both A and the intersection of the closure of B and the closure of A intersected with B are empty. That is, if no point of A lies in the closure of B and no point of B lies in the closure of A. A set E that's a subset of X is said to be connected if E is not a union of two non-empty separated sets. And all of these concepts we're going to learn what they mean, like open cover, closure, and so on. So we'll be learning what all of these things mean in more detail, but just to give you an example of connected, if we have two sets, minus infinity, comma, the square root of 2, and the square root of 2, comma, infinity. So these are two open sets, right? Everything less than square root of 2, everything greater than the square root of 2. So these two sets are separated in both the real numbers and the rational numbers because closure means every limit point. So in this set, the square root of 2 would be in the closure of this set, but it's not in this set, but it's also not in this set. So these two sets are separated in real numbers and in rational numbers. But the rational numbers, the union of these two, covers the rational numbers entirely. There's nothing missing from this, right? This set unioned with this set equals all of the rational numbers. It does not, however, equal all of the real numbers because the square root of 2 is missing. The square root of 2 isn't in the rational numbers, so it's not missing from the union. So this is the problem. The rational numbers are not connected because the rational numbers can be represented as the union of two separated sets. The real numbers cannot be represented by the union of two separated sets. So the real numbers are connected. And that issue is what's missing from the rational numbers. So although rational numbers are continuous, according to our textbook definition, they're not connected. The textbook, because it's only talking about real numbers, allows itself to just assume that the number system, the real numbers, is connected, because real numbers are. So it's not an issue. But in order to prove the intermediate value theory and hence L'Hopital's rule explicitly, we need to actually prove that the real numbers are connected, and then that will lead us to the intermediate value theorem. So, as I said a minute ago, a whole lot of mathematics, the way it works, what mathematics is you take some set and then you add some rules or relations to that set. So groups add an addition operator to a set. A field adds addition and multiplication. Ordered field adds an order to it, and so on. So the metric space takes a set and adds a distance relation to the members of the set. So what is a topology then? If mathematics takes a set and adds some structure or rule or operation to it, then what in the world is that definition of topology doing? What is being added to that set? Let's look at it again. So here's the definition of topology. What is this definition adding to this set? What this is describing is open sets. So boiled down, and the concept of an open set is the concept from which everything else in topology is defined. So when someone asks you, what is topology? There are two answers. One is it's the study of bras and cups and donuts. And the other is it's the study of open sets, period. I've taken a whole class in topology, and that was never explicitly stated. And we went through an entire chapter working with these these rules. And you understand that it's about open sets, but without really understanding, but that's what we're talking about, that's what we're doing, is looking at what happens if a set has a concept of an open set added to it. So this is astonishingly far removed from limits and continuity, right? But these three bizarre conditions that make up the bizarre notion of a topological space, what they're describing is an open set. If you go through them, you'll see this is true of open sets, like in the real numbers, that the empty set and all of the real numbers are open sets, and the union of the elements of any subcollection of T is also in T. What that means is that it's so weird because a topology is a collection of sets. It's not a collection of elements of the set X. So the topology is making a new set, which is a collection of subsets of X. Okay, so what this means is that if you take the union of two open sets, the union is also open. 3 says the same thing about the intersection of elements of the topology are also in the topology. And that's how you define what an open set is. So, given that, now we understand what it means when we say that a metric space is a kind of topology. With distance, we can make an open set. We just did. If we have, when we're looking at limits, if we have, x minus delta, x plus delta, that is an open set, right? Or I should say, let's make this so it's right? This is an open set of x that's everything less than a distance of delta away from A. So by adding distance, that allows us to create topologies. So that's why a metric space is a kind of topology. It's the kind of topology created by using distance. So we're talking about the distance around a point. So topology as an area of math is not necessarily devoted only to metric spaces. There can be topological spaces that are not metric spaces. But all the concepts that we're going to be talking about here, they all operate in the context of metric spaces. and so are a kind of topology. But when we talk about open sets, compact sets, connected sets, and so on, those are all concepts of topology that are broader than just metric spaces. So compact set, for instance, is not a concept of a metric space, it's a concept of topology. And metric space is one example. Calculus and real analysis operate within the context of metric spaces. So following Rudin, we will be learning these concepts for now, specifically in the context of metric spaces, even though they're actually even more broad than Rudin examines them. Okay, so that's it. That's what we're going to be doing now. Next week, we're going to finish up with continuity and look at the calculus textbook version of continuity. And then we're going to go back to the basics of topology and follow chapter 2 of Rudin until we're in a place to prove the intermediate value theorem. And then we'll go from there to prove L'Hopital's rule. All of that just so we can play more with indeterminate forms. So please come back. This is going to be fun and interesting, and I think it's going to be the most challenging thing that we've done so far. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.